There are probably 2 million asteroids in our solar system.
The reason that Psyche is unique is that it is metal-rich.
It's believed that it may be a remnant core of an early planetesimal.
One of the ingredients that went into making our Earth, and one that we cannot see any other way. And it would be the first metal object that humankind has ever visited.
Studying the evolution of a planetary body is a detective story.
I think the only thing we know is that it's not going to look like what we think it's going to look like, and it's going to be really interesting, whatever we find.
Space is always more amazing than we can imagine with our minds.
Good afternoon. My name is Megan Cruz, and thank you so much for joining us for Psyche's NASA Social Panel. The Psyche spacecraft will visit an asteroid also named Psyche. It will be the first mission to explore not a world of rock or ice, but one made mostly of metal. How cool is that? Now, liftoff on a SpaceX Falcon Heavy rocket is targeted for tomorrow, October 12th, 10:16 a.m. and 49 seconds on the dot Eastern Time. Now, today's audience in this briefing room here with us is a group of digital content creators visiting Kennedy Space Center here for a NASA social. And as part of that, they're going to get a behind-the-scenes tour. They actually did get it earlier today, and they're now meeting these interesting people that I have sitting with me up on this panel. So to my left here, Bob Cabana, NASA's Associate Administrator. We also have Eric Dernberg, Dynamic Environments Analyst for the Launch Services Program based here at Kennedy. We also have Haley Bates Terra-Savage. Did I say that right? Yeah. Okay. Payload Systems Engineer at JPL, Jet Propulsion Laboratory in California. And we also have Malcolm Wright, a technical lead for the lasers on the Deep Space Optical Communications Experiment, or DSOC, which is flying with Psyche. Now, we're going to be taking questions live and also online. So anyone online, you can drop hashtag #AskNASA in the comments section, or really wherever you're watching this, and then we will try to answer as many questions as possible. But for now, let's kick things off. Bob, you have quite the resume. You are NASA's Associate Administrator, as we said. Before that, you were the Center Director here at Kennedy for many years. Before that, you were you were a shuttle astronaut. So what don't you do, and what do you love about NASA that you've been here in so many different roles all these years?
I think what I love most about NASA is the mission and the people. You know, I was really blessed to have gotten to fly in space. But, you know, most of what astronauts do is not fly in space. It's support other NASA missions. And to be part of, you know, the agency that's been #1 in the federal government 11 years in a row, why is that? It's because of the people and who we get to work with. It's just an amazing team, and the mission that we have. I mean, we're making a difference for humanity, not just for our nation. And you look at all the exploration. I think what's really cool is, and I know we're going to talk Psyche, but being a pilot, you know, when I was in human spaceflight, it was pretty much rockets in human spaceflight. But being the NASA Associate Administrator, I get to see NASA's whole portfolio and all the cool stuff we're doing. Aeronautics, you know, the truss-braced wing on the sustainable aircraft, the X-59 Quest, the supersonic aircraft that's going to have a low boom, demonstrate that. Just the science that's being advanced, everything that we're doing, going back to the moon, onto Mars with the Artemis program, it excites me every day. I mean, that's what's coming to work is all about, is to work with an amazing team of brilliant people and get to do really fun things that are making a difference, Megan.
Yeah, and I'll keep it with you for just a second. What are you most excited about for Psyche? I mean, it's a really unique mission.
Hey, yeah, you heard me say it before. Who doesn't like heavy metal rock, you know? And I think all the missions that NASA's done to asteroids and stuff are other bodies in our solar system. We've gone to things that are rock or ice, but this is the first time we've gone to something that's heavy metal and what we learned from it. And I'm going to let the experts talk about that from JPL. Haley, you got that one. But, you know, I think it's to be able to go to something that's 2.2 billion miles away and learn about it and how planets are formed. You know, most of what we do is to help us here on Earth and to understand how we were formed, what our future is. Is there life? You know, the quintessential question is there life in the universe beyond our home planet? And learning all these things, I think, it's really awesome. I mean, what's not exciting about that?
Yeah, absolutely. Okay, Eric, so you're with Kennedy's Launch Services Program, also called LSP. LSP is the one who's responsible for getting Psyche where it needs to be. Can you tell everyone a little bit more about the program and what you do there?
Yeah, sure thing. So as you said, Launch Services Program, we're in charge of managing the launch services here at Kennedy Space Center. This is where we're headquartered, but we also have launch sites across the U.S. and abroad where we're able to get NASA spacecrafts, all these interesting scientific equipment, up into space safely, on time, on budget, and all that good stuff, right? So that's our main bread and butter, and we do that in a couple different capacities, some advisory missions, some main flagship missions, and Psyche being one of those. And we partner with those spacecraft community, like the folks here at JPL and others, to get that scientific equipment up into space and where it needs to go. So to make that happen, we partner with launch services, so launch vehicle providers. Those could be anywhere from a SpaceX Falcon Heavy to an Atlas V to an Antares from Northrop Grumman. So we have a lot of different launch vehicle provider partners that we're able to go and procure launch vehicles from and make sure that they are the right size, the right fit for a certain mission, and get that up to space safely. So me specifically, I do dynamic environments, is my title. So that's kind of it's in the overarching field of structural dynamics. So if you guys sit on a chair, right, so that chair having to withstand, you sitting on it, that's more of a strength analysis. If you start shaking around and moving it, that's vibration. That goes out from static into dynamics, moving around. And so anything that moves on the rocket is really my main bread and butter, making sure that we do the analysis to make sure it doesn't fail, and that it works and does its job successfully to get everything up to space. And the three main fields there being acoustics, shock, and random vibration. So that's kind of, in a nutshell, what we do at LSP and what I specifically focus on. So.
Tell people more about an acoustic test, because I've seen it and it's super cool.
Oh, I mean, they're the best. I mean, honestly, the JPL folks have it nice, because so we're here at Kennedy, so we'll go out and travel to some of these acoustic tests, but as part of the launch vehicle decide, make sure they're hitting the right levels and those kinds of things. But ultimately, the spacecraft folks that are building the hardware, they're responsible for those tests. And it's amazing. I mean, you get this huge spacecraft in this chamber, and you just play heavy metal rock at it. No, we have specific levels, and it's a very technical test. But beforehand, to test out the systems, oftentimes they will do. It is just a giant speaker system at the end of the day, so they will do some tests with a little Led Zeppelin, some other stuff in there, just to check out everything. So, awesome tests, very dynamic, no pun intended, and there's a lot going on, and there's a lot of things that can also go wrong, right? So that's where the spacecraft team and the launch team work together to make sure that we have a successful test, and we do a lot of planning to make sure that's executed, to the T. So
yeah, that's an awesome job. Okay, Haley, as we've been saying, you work at JPL. You've worked with all the instruments involved with the spacecraft. So tell us a little more about that.
Yeah, so I'm a payload systems engineer at JPL, and my team is responsible for basically making sure that all of the instruments are at home on the spacecraft and well accommodated, and we know how to use them. So the payload is a bit distinct from the spacecraft. So the spacecraft is the components that make sure we can get from Earth to Psyche. We know how to point, we can charge our batteries, the main computers, that's the spacecraft system. And the payload system is all the instruments. So I've been lucky enough to be able to work on the gamma ray and neutron spectrometers, the magnetometers, DSOC, and my primary responsibility right now is with the imagers. Throughout the timeline, the build timeline and integration, we make sure that we work with the scientists to make sure that the hardware is actually doing what it needs to do and performing well enough that we can make the measurements that we need to when we're at the asteroid. We make sure we know how to use it and work with the operators to develop their sequences and make sure that we can actually execute the science that we need to do. And then, of course, all of the other interfaces, so everything from dynamics testing to thermal vacuum testing to electrical to thermal and everything in between. So I've had the chance to kind of work with all of those various areas, and it's been pretty exciting.
Yeah, that's cool. So there's three main Psyche science experiments. Can you talk a little? You mentioned the names. Can you tell a little bit about what each does?
Yeah, of course. The main investigation here is trying to understand what Psyche is. If it's a planetary core, and if it's not, then how did it form, and what does it tell us about the formation of Earth or the other planets? And the way we're going to do that is with the imagers, the gamma ray and neutron spectrometers, and the magnetometers. So we're going to map the surface, identify interesting features on the surface, try to characterize the ages of different regions, and we're going to combine those maps with the gamma ray and neutron spectrometer composition measurements. So specifically, we're looking for what metals is Psyche made of, what else is it made of, and what ratios, and what does that tell us about how it formed and how it cooled, if it cooled from the outside in or the inside out. And then the magnetometers will help measure the magnetic field. So if it has a magnetic field like Earth's, what does that tell us about its formation? If it doesn't, is that significant in any way? And all three of those kind of combined together will help tell the story of what this actually is.
Yeah, that's what I love, that all those three instruments work together to answer this really huge question that scientists are really going to have a fun time discovering. Okay, hitching a ride with Psyche is DSOC, and that's what Malcolm's here for. You're the, again, technical lead for the DSOC downlink, right? Talk about why communication in deep space matters.
So on any mission you have, you're worried about getting the science back, and that's what Psyche's want to get the science back from the asteroid. And so what we're doing is optical communications, taking it from the RF, microwave, radio spectrum to optical, just like you do at home, going to the fiber, having high data rates. And so the whole point of doing the free space optical is sort of like having fiber to the home, although there's no fiber, so we do free space. And so we're taking the same sort of technology that's in the commercial realm to validate it, so we can modify it to work on the spacecraft. And so any instrument wants to have, any mission wants to have more science return. And so if you have a smaller system, you get more power back through the optical link. Therefore, you can have more instruments on there or less time involved on the actual mission. And so you're spending more time targeting different instruments or different missions to get the data back. So optical overall gives us that ability to increase the science return over in the long term, as well as on that mission particularly.
And what's unique, because we use laser communications now, right? This test is the first time that we're going beyond the moon.
Right. So we actually did some experiments over the last several years at JPL and with NASA. We did one with the Lunar program, the Lunar LLCD, Lunar Laser Comm Demonstration, which demonstrated high data rate coming back from a lunar orbiting spacecraft. Then we did one with the ISS on the space station, just showing the ability to point and track the spacecraft as it goes across the sky and compensate for the atmospheric effects, because you get a lot of perturbation from the atmosphere when you have optical signal, so you'll be able to correct for that. And at the same time, we've transitioned to the GEO one. So we have another experiment been going on right now called the LaserComm Relay Demonstration, which is from a GEO satellite about 40,000 kilometers. So relaying data from 2 ground stations, high data rate, gigabit per second type links, as well as ones from LEO doing high rates, 200 gigabits as well from a T-Bird, another recent demonstration. So this is the first time going past the moon, which gives us a lot more challenging because you've got a lot further range. That means you've got a lot of different powers, and pointing becomes a big issue. You're talking very fine, very challenging pointing for a lasercom beam, because you get a very fine pointed signal, so you have to be very accurate. So all those technologies sort of playing into building us up to this first deep space optical comm demonstration.
Cool. All right, it's time to take questions. Why don't we start here in the room? Who wants to ask the first question of our awesome panel? Okay, well, okay, because I have one too. Go ahead.
I'm Sean with the Museum of Flight.
Sorry about that. Forgot to mention to wait for this mic. Go now.
I'm Sean with the Museum of Flight in Seattle. We work with a lot of students, a lot of elementary, middle, and high school students, and they can face a lot of challenges, and they can fail at those challenges, and that can get discouraging. So I'm just wondering what words you would have for them about failures you've encountered over the course of this mission, and what you've learned from them, how you pushed past the that drive to stop and just keep on going.
Great question.
Well, I'll start. I'll let them talk about the mission, but I got to talk to those kids, because, a lot of folks might say, wow, I'd like to be an astronaut. That's kind of a hard goal to set. There's a lot that you have to accomplish before you reach that point, before you're qualified. And there's a lot of steps along the way. And I will just say, I never made any of those steps on the first try. I didn't get into pilot training on the first try. I didn't get into test pilot school on the first try. I didn't get in the astronaut program on the first try. But I didn't give up. And I think it's really important that you set a goal for yourself and you work toward it. But there's intermediate goals that you have to meet along the way, and you work toward those. Do something that you really enjoy, that you're passionate about, so that, first off, work's not work. You enjoy it, like working here at NASA. All right, all that we do. And studying's not hard in school if you're doing what you enjoy. So apply yourself, do well, and if you don't get it on the first try, don't give up. Set that goal for yourself and work toward it. And then when you achieve that goal, then you can set a new one and move on. And even if you don't make that next goal, you're still doing something that you really enjoy and you're making a difference. So I think it's really important to do what you enjoy doing, what you're passionate about, that you have a talent for, and then obviously don't give up. Be persistent. Yep.
Yeah,
But we've had setbacks on the payload. Haley, tell us a little bit about some of the things that went on with Psyche getting to where we are.
Oh man, so without getting into too much of the nitty gritty, I just want to failures are a normal part of this process. I mean, we're working on hard things, and that's never going to go off without a hitch completely, right? And people are human too. People aren't perfect, so that's just a normal part of the industry, is dealing with not even necessarily failures, but failures and challenges and solving problems that have never been solved before. It's a natural part of the process, and I think that everybody here would probably tell you a story that wasn't particularly straightforward, that had winding paths and up and downs, because that's just normal. But a lot of what you hear when people talk about it is the polished version, is the version that seems to make sense from start to finish, and that just really isn't true of pretty much anybody that I know. But I mean, with Psyche even, I mean, we had the launch delay last year that the whole team really had a tremendous effort to push through, and at the end of it, we are better off for that than we would have been if that hadn't happened. So that actually became a big strength, and I think we're going to be a lot more successful because of it.
It's also why we test. We want to find failures in our tests so that we can correct the issue and not have that problem when we get in flight. And that's why testing is so important as we develop the payloads that we fly.
And President John F. Kennedy said this, I mean, we do things not because they're easy, but because they're hard. And how fulfilling is it when you accomplish something hard? So, so think about that.
One more thing too is just what I've noticed at NASA and now at JPL is being on the right team and having a bunch of people to support you. That's a key factor, I think. If you're doing it on your own, you really get challenged. But being around the team of people, everyone can pull the weight and really understand different aspects is a key part of the team environment here.
Any other questions here in the room? Go ahead. A mic's coming around to you now.
Hi. Hi there. Our job as NASA social representatives is to teach our audience a bit about the mission. So, in general, tell us about the mission. Where is it going? How long is it expected to last? And just for my own personal curiosity, what are the chances of an extension at the mission's end? And are you planning on crashing it into the asteroid or just leaving it in orbit forever? Thank you.
Anyone want to take that?
I'll talk a little bit about that. So the Psyche mission is going to the Psyche asteroid. It's called 16 Psyche. Our cruise is about 6 years long. We have a Mars gravity assist along the way. And once we get to the asteroid, we will be captured by the asteroid's gravity and be orbiting the asteroid for the duration of the mission. We have a couple different science orbits, or what we call, where we start further out and then move closer and closer in and get better and better data as we understand even what this object is shaped like and other properties of it. And at the end, when we switch the orbit to 90 degrees so we can measure the poles and get a bit of a different view of it. And we're expected to orbit the asteroid for about a year. That's our main science phase. And as far as the extended mission, expectations of an extended mission is, there's no confirmation of that quite yet, but I know that there's a couple of things that we'd be excited to do after that year period. So even from my own perspective, I work mostly with the imagers, and we have a pair of 2 redundant imagers, and we only ever expect to operate one at a time until we've gathered all of the data that we need to. We can stamp it, say, done. And we do that to protect the redundancy, so that if one of them encounters a problem, we have another as a backup. But after that year long, we very may well turn them both on at the same time and see if we can get some binocular data or things like that. I haven't heard any plans to crash it into the asteroid, but hey, if there's something interesting we find that might make it worthwhile, then hey, that would be awesome.
I also have to give the folks out at JPL, you want cool math, give them credit for the amazing trajectory analysis that they do. It's just absolutely phenomenal when you look at all the different science missions and how they utilize gravity assists off the planets for limited thrust and everything else. That is one amazing team out there that does the trajectories for our science missions.
Yeah. Absolutely. So we have a question on X. This is from Rachel. What does DSOC stand for? And I heard it is hitching a ride on the spacecraft. I said that. What does that mean?
Sure. So DSOC stands for Deep Space Optical Communications. So it's really NASA's first, as I said, deep space as opposed to other optical communications. And we're a secondary payload. So we're sort of like a payload like the other instruments, but we're our own self-standing experiment. We're actually just operating for the first 2 years on the cruise. So we're actually not going to be there, but we keep working. But if we get out to Psyche in 6 years, but our goal is just to demonstrate that capability over the first 2 years of the cruise mission.
And I'd also like to add the communications from Psyche to bring the data back are not dependent upon the deep space optical comm system. This is a technical test just to ensure that we can do optical communications from deep space. So when it's not used anymore, it's okay.
And what I think is cool is DSOC is future-leaning tech. I mean, we're going to use it for future missions. We're talking about our Artemis missions to the moon, to Mars. Can you talk a little bit about that as well?
Right. So we're actually putting the system together for the Artemis one. It's a smaller terminal because it's closer range, and so we're doing the ground station and same technology, multiple lasers on the ground, a single laser transmitter that will fly on the Artemis spacecraft, I guess. It's not on the trunk. And so we'll be doing that experiment to send back basically like HD data, high-definition data, high-resolution images for the astronauts on the Gateway mission or on the whole orbit. So it's like a 10-day mission, I think it is, that we have. That's coming up end of next year right now as the current launch.
And actually, I want to talk a little bit more about trajectory. You mentioned this. I mean, so when LSP launches things, they're uncrewed spacecraft usually, and they usually end up orbiting around the Earth. But this is going so much farther. Was it complicated to figure out that trajectory? And also, did that dictate why we ended up going with a Falcon Heavy?
Yeah, for sure. Yeah, so I'll preface this with, I'm no trajectory expert, but yeah, definitely I would say one in every handful of missions we have, an Earth escape kind of like situation. So in this case, I believe Psyche is going and doing a Mars gravity assist. So to accomplish that, we're actually kind of, the launch vehicle is responsible for getting it up outside of the Earth orbit and getting it on its way, heading towards that first mission objective. And the second stage will separate once it gets up into space, and then the spacecraft is on its own. It will use its propulsion system, which I think is like a electric propulsion system, so a very low thrust, very efficient propulsion system to get it the rest of the way over around Mars, do the gravity assist, the complicated trajectories that they work on at JPL, and off towards Psyche eventually. So yeah, the on the launch side, it's really important to be able to get up a spacecraft that's the size and weight of Psyche to get to that Earth escape kind of velocity. And in this case, we are, the best option that we had was a Falcon Heavy launch vehicle. And that's all for you guys' benefit, right? Because tomorrow at the launch, you'll be able to see these two massive side boosters come back and land, which will be amazing. You'll get to hear sonic booms with these. Besides various, Air Force testing and things since the last shuttle landed, these are some of the first, sonic booms that we're hearing in this area. So it's since Falcon 9 started landing and now Falcon Heavy as well. So seeing these two boosters come down at the same time is just an amazing sight. So for those of you that haven't seen it yet, I think you're in for a treat. So, but yeah, it's definitely a complicated mission, and it's not one that it's one that will require the use of something with more thrust like the Falcon Heavy. So
I'd like to add to what Eric said. The other thing that's cool about this mission, this is the first time that NASA has used electric Hall thrusters for a deep space mission. They've been used in low Earth orbit before, but this is the first time on this Maxar-built bus that we're using them for deep space.
Yeah, that's a really cool one too. We could talk more about that because that's a really cool one.
Maybe just real quick, another first is our first launch with Falcon Heavy, which I think they might have mentioned earlier, but it's worth, with NASA and our partnership with SpaceX, I think it's a big milestone to get Class 3 certification on a launch vehicle that has the capability that Falcon Heavy does. So I think that's another big, long effort that the Launch Services Program had to go through in order to get to this day with launch tomorrow. So
that's a big mission. You guys are in for a treat. All right, this is a question from YouTube. We'll start off with Bob. This guy says he is almost 76 years old and recently retired from teaching. Am I too late to enroll in the astronaut training program? And the question for everyone else, what was your path to getting to your job?
So first off, there is no age limit to be an astronaut. all right? As long as you can pass the physical and are healthy and meet all the other criteria, you can apply. So I wish you well. Yeah, I think I shared my path, but you know, all I ever wanted to do since I was a little kid was fly jets off aircraft carriers, and I was fortunate to get into the Naval Academy, and one thing kind of led to another. But that gets back to, you know, I was very fortunate to get to follow my dream, and not many kids get to do what they wanted to do since they were 5 years old. But I think, again, having that passion and desire and not giving up when things don't go, that's really important. But coming to NASA was a dream. When I reached my retirement from the Marine Corps, I did not want to leave, and so I took a civil service position at NASA, and I still love coming to work every day.
Yeah, well, I'll try and be a little bit concise, but I also do want to circle back to the kids and the failure question earlier. You know, it's when I was growing up in South Florida, I was always messing and taking apart cars and unscrewing things, and my dad at a young age realized that this guy's got an interest for just breaking things, and I wasn't great at putting them back together, but I loved breaking them apart and seeing how they worked, and so I think he definitely was a big inspiration to be able to go into the engineering field. But I originally wanted to be a pilot. I wanted to fly planes, and so what ended up happening is later on I realized that I had more of a passion for the engineering side of things. I went to University of Central Florida here and studied aerospace engineering, which for those of you that aren't in the field, a lot of the times a lot of schools will focus on aeronautical and astronautical engineering, so outside the Earth's atmosphere, inside the Earth's atmosphere, but it's the same engineering degree. And so I realized then that instead of working on planes and being an engineer for planes, I actually was much more interested in space. And I needed to follow that passion because that's what we talked about earlier. You can have goals in life, but I think you really need to follow your passion and be willing to pivot when you have certain areas that you just don't feel comfortable with or you don't really enjoy anymore, you know? So that's kind of how I got here. I went to UCF and decided that space was really cool. I started working on the GPS program here at Kennedy Space Center for the Air Force, and after I was done with that, I decided, you know what, launch vehicles is really the cool thing. And so I was very much, I had more passion on the launch vehicle side, and you know, that's where I ended up. So I think it's important to kind of follow that passion and not be discouraged by getting into something that you're like, this is exactly what I wanted to do when I grew up, and just being unfulfilled with it, you know, being able to kind of pivot. So.
May I interject?
Of course.
I got one quick story. You made me think of it.
Yeah, you're welcome.
Don Pettit, Dr. Don Pettit, he got selected to be an astronaut on like his 5th try. Just brilliant, great astronaut. When he was like 8 years old, his brother went to the junkyard and bought an automatic transmission and brought it home and gave it to him on his birthday and gave it to him to take apart and figure out how it worked. So.
Well, for those of you that haven't seen it, look up Don Pettit's video of him taking apart his watch and fixing it on the station. That's amazing, and it's awesome to see little screws floating up, and he's like, "Oh, let me secure that with a piece of tape."
Oh, that would drive me crazy.
That's a lot of fun. Take a look at that. Yeah.
I'd be panicking. Go ahead, Haley.
Yeah, so I am trying to be careful telling this story so it doesn't sound too neat, like as we were talking about before with the failures and such. But when I was younger, I knew I wanted to learn something about the world, but that's not really applicable to a specific job. But I knew that's what I wanted to do. I wanted to help learn something. But I also couldn't see myself in a role where I wasn't also making something. So I combined those two things where we wanted to make something that helps us learn something. And there's a lot of industries that could have been applicable to, but we know so little about space that I've always been kind of drawn to it. So, you know, building something that helps us learn something about space seemed like a pretty logical fit, but it wasn't always NASA for me. It is now, but I was lucky enough to go to MIT, and I studied aerospace engineering and planetary science there. And I mean, just to talk about failures, I took 5 years because I failed calc, but I ended up picking up a double major and a minor in creative writing out of that, so you make the best out of your failures. And I knew I wanted to go to JPL because a lot of cool stuff happens at JPL. Tried to get internships for 3 years, and finally they selected me in my last year. And when I was there, I think I cold emailed 50 different supervisors, seeing who would take me on full time, and ended up in exactly where I wanted to be. And if there's anything that came out of that, it would be, don't be afraid to tell yourself or other people what you want. I think there's a lot of people who are humble and they're like, oh no, thank you for this opportunity. I appreciate it, and they're hard to, it's hard for them to ask for more. But I think being able to say to yourself, this is what I want, and be able to tell that effectively to the people who can give it to you is one of the ways that people really find their path. So.
Yeah, find your path for yourself. Great advice. Malcolm, go ahead.
So I grew up in New Zealand, way down there. There's no space program when I grew up, and so I always wanted to come to the space program over here. I always wanted to know why things worked, how they did. So I studied physics and came over here for grad school and got a PhD in physics. And I wanted to study light because light was like a reflection of what the world was like, what God was like. And so lasers were the coolest thing. And when I was a kid at school, knowing that you could put electricity through a crystal and get light out, like what? So lasers, I did quantum optics in grad school, and then worked in laser physics in the Air Force lab making high power lasers. And then I wanted to be a part of a team. I didn't want to do just research on it. And so I wanted to actually apply this to a field where I could talk about it and actually work with a team of people, because people makes it fun. And so then I applied to come to JPL through a connection. I heard a professor using the same sort of lasers for free space communications. And so I was like, well, that's cool, because I'm a physicist, not an engineer. And growing up, that's a big difference, you know. But at the time, I was like, okay, I want to actually do engineering. And our group is actually a bunch of physicists doing engineering. And so we're just taking the technology, understanding the physics behind something, and then applying it to a mission, to something that can be used, was really the fun part of JPL. It's taken 20 years. I came like 20 plus years ago to work on a mission, and it goes up and down, and then 25 years later, we're flying the technology that I've been investing in for the last several years. So that's sort of a circuitous path, but that's where we've landed in this fun place.
Show of hands, who thought they'd be here at this moment talking to a group about Psyche logic today? Yeah, but it's so cool, right? Like, life is funny like that. All right, last call for questions in the room. Oh, we have a lot of, oh gosh. Okay, over here.
So this, of course, is what we think Psyche is going to look like. But behind the scenes, have you all created your own little pictures of what it's going to look like? Is it going to be this sphere, or is it going to be something else?
I'm not super creative, so I just trust what the artist's rendering, but I'm sure maybe some others have some fun ideas.
Honestly, the rendering that is all over the place of the Psyche asteroid is a pretty well-educated guess. I mean, even the surface, the crater formations, things like that. Like, the crater formations have some interesting ways that they show the material kind of jetting out. And I believe that the artist actually got inspiration from that, from a test that was done where they took a block of metal of what we think Psyche is made of and essentially shot a gun at it to see what it would spray out. And so a lot of those different, I mean, not, yeah, don't do that, yeah. But all of that has been lumped together into what we think it looks like. But of course we don't really know until we get there. And we've been so surprised before in previous missions where we think we have a good idea of it and we get there and it looks nothing like it. So personally, I think it looks like a meatball.
Over here.
My name's Kate. I'm live on my Twitch channel right now, so these are questions from my Twitch chat. It's a two-part question. One, how much data do you currently have on Psyche? And once you get into orbit and stuff, when do you expect the first data reports to come back?
Yeah, sure. No, I just wanted to make sure other people had the chance to. So since the Psyche mission was selected to fly, people all over the world have been pointing telescopes towards Psyche, the asteroid, trying to understand it better in preparation for this mission. So how much data do we have on it now? A lot more than we did when we first started. So we have good measurements of the mass and the radius, so we understand those things pretty well. We have a good idea of kind of the rough shape of it that we'll probably refine. We'll refine as we get there. And that sounds straightforward, but that was a lot of effort to get to. And as far as the first science data we get back from it, we'll be getting data kind of all the way there. We have some experiments at Mars and such, but the first data of Psyche we'll get back is as soon as we can take a picture of it. So a couple years in, but.
Okay, over here. Oh, give me 1 second. Let's just get a mic to you. Yeah, you, but we're just going to wait for a mic here. Okay.
Hi, Scott Young, Manitoba Museum in Winnipeg. I wanted to ask about the Mars flyby that's seems like the first big milestone after launch. What kind of experiments are going to be happening around then? Will you be using the imagers on Mars and things like that, or are there navigational trajectory changes to make or things like that? What happens in that flyby, and what is the timeline of that flyby?
You know, that's a really good question, and I'm not as familiar with the Mars investigations as I am with the Psyche investigations, so I'm kind of speaking very generally here, but we'll be doing some gravity science and also using the magnetometers around Mars. I'm not sure of exactly the kind of imaging and stuff we're doing. I'm not aware of any specific investigations there. I think it'll depend on a couple different things, and those decisions will be made kind of after launch. But yeah, I'm sorry, I don't have a ton more on that. It's a good question, though.
There was another, two more hands. Okay, we'll go to the, I think her in the back had her hand up first. Thank you, Frankie.
Hi, I'm Lisa Novotny, first grade teacher from Loyalsock Township School District, and I have a question about the neutron spectrometer. Can you elaborate more about that?
Yeah, so we're taking both a gamma ray spectrometer and a neutron spectrometer, and what happens is radiation from the sun hits the surface of the asteroid, and these different particles interact with the surface and with the different materials in the surface, and reflect back off. And the speed and frequency at which they reflect back off is indicative of what they were interacting with in the surface. And we can get deep, like even several meters deep within the surface, and see those particles bounce back. And we detect those particles, they hit our instruments, and by understanding the speed and the frequencies of them, we can back out what they were interacting with on the surface. So the neutron spectrometer picks up the neutrons that reflect back off, and then the gamma ray spectrometer gets the gamma rays, and it uses a ultra high purity germanium crystal to detect the different particles. It's one of the most pure germanium crystals on the planet, soon to be off the planet, and it's some really, really cool technology. Yeah.
Okay, and the last question here.
Hi there, Brooke Owen from Arizona Science Center. This is such an innovative mission and it's really exciting. What are you most excited about?
Who wants to go first?
I'll go real quick. Obviously launch services, big launch guy. We've already kind of covered that, right? So I'm really excited for just getting to see up close and personal with the Falcon Heavy launch vehicle. Our first milestone. It's also our first time we had to, during my specific field, having to do a reuse review because we have multiple boosters that we're reusing on this one mission. So we've done them for DART, IXPI, and other missions before, where we have to make sure that the hardware is ready for another flight. And not only ready, but just as good as brand new hardware, right? We're not accepting any additional risk by flying with a flight-proven booster, and that's exactly what we've done for the Psyche mission. And having to do that for 2 boosters at the same time, just a lot of effort by the whole team at LSP. So it's going to be really exciting to see those used boosters fly up, break off, and get Psyche up to where it needs to go. And I'm just kind of excited for that launch day and spacecraft separation, So.
Always fun to see a launch.
Mm-hmm. Yeah, doesn't get old.
No, never. I'm excited to learn about Psyche because it helps us learn about us and our place in the universe. Always learning. We should always be growing and learning. But I got to admit, the Deep Space Optical Comm, the folks out at JPL that run our Deep Space Network, this is critical to get all the data back from all our science missions, and having a capability to do that faster with a higher data rate is going to be crucial as we move forward, especially for the human side, going back to the moon and on to Mars. The amount of data that we're going to have to get back from the moon on our lunar missions, it's huge, and that impacts our ability to get data back from our other science missions, which are equally as critical, learning about all the cool stuff that's going to be going on. So if we can prove deep space optical comm and make it into an operational system, that's going to be a great breakthrough for deep space comm out at JPL.
I'm excited to get a photon back from past and make sure I was responsible for the laser, the flight laser, so just to see it working and sending down data would be huge.
Yeah. Haley?
Man, I don't think I can pick just one. There's so many firsts with Psyche, and it's just really such a cool program, and it's been so cool to be involved. But I think the first pictures we get back, I'm biased because I work on the cameras, but I think getting that first picture back is just going to make it all feel so much more real. And we have years to wait, but.
Yeah, I think we've established that we're all very passionate about what we do, so.
Well, awesome. Thank you guys so much. Thank you to everyone who asked questions, either in person or online, and then thank you as well to our panelists. And now set your calendar or your alarm for Psyche, again scheduled for tomorrow, October 12th at 10:16 a.m. Eastern Time aboard a SpaceX Falcon Heavy rocket. Launch coverage will begin at 9:30 a.m. Eastern, and you can watch that on nasa.gov/live or on all our social media networks. So we hope you can join us for, again, what should be an exciting mission.